Okay, so let's continue the discussion about logarithmic function. Remember that if we have e to z equal to w, then the solution set is log absolute value of w plus I times the argument of w plus 2 pi and k. K is an integer. Right? And we already show that if we have like f, a branch of a logarithmic function, logarithm function, then all logarithm function can be written here we need it on a connected open set, connected open set. All logarithmic functions can be written as f of z plus 2 pi ki. You just add a certain constant numbers, you get all other logarithmic functions, right? And we also know that logarithmic functions is analytic. And the derivative of the logarithmic functions is 1 over z. Okay, so by this we are going to define the so-called the principal branch, the principal branch of the logarithm. The principal branch of logarithm, you need name the domain. The domain is on C, but without non-positive real numbers, right? So this is a complex plane, including 0 and all the negative real numbers. You just cut them. Cut them means we don't consider them. And then all other parts, this is open and connected. And this is the domain of a principal branch of the logarithm. And we define this, let me see, yeah, L of G, log Z to be, this is Ln, natural log of the absolute value of Z plus I theta. Plus I theta. What is theta? Z is here. Z is REI theta. If we have this polar representation of complex numbers, Z is REI theta. This theta is argument of W. You see, this is argument W. And because we cut it along the negative real axis, so you can imagine that your argument can only be like this. You go clockwise or you go counterclockwise. You go counterclockwise is positive pi. You go clockwise is negative pi. So theta is between negative pi and positive pi. Okay, theta is between negative pi and positive pi. This is, well, with r, we should write is ln of r plus I theta. ln of r plus I theta. This is natural log for the real analysis. Okay, so we got all the required properties or definitions about the logarithmic functions. All right. Again, remember that logarithmic functions means exponential of f of z, which is exponential of log of z is itself. Okay. The other thing is that, remember, when we have a to b's power, or in the calculus, we can get exponential log a to b's power, and then we get exponential. You apply the property of the logarithmic function in the real calculus. So you move b forward is b times natural log of a with composed with the exponential function. This is the identity in the calculus. We can understand the arbitrary power function by this way. So here we're going to follow the same process and define the general power function. We define the general power function. So we first, that's the next definition. So let f be a branch of the logarithm it's not necessarily the principal branch, just whatever branch of a logarithm. It is on an open connected set G, and let B be a complex number, whatever complex number. Let B be a complex number. All right, and then we define G, function G from the set G to complex number by G of Z equal to the exponential of this B times f. F is a branch of the logarithm. Okay, so how do we come up with this expression or composition? It's exactly this: exponential of a constant number times the natural log of a. Natural log of a is this f of z. Okay, by this way, we define z to b to be this. We define z to b to be this, and usually, I mean, well, up to here, it's general definition for whatever open connected set and whatever branch of a logarithm, we can always define this. But if we want to write z to b, we want to make sure we choose the principal logarithm. Okay, so this is the general definition. It can be used to define the general branch of the general power function. But once we write it in the special symbol, we want to choose it as a principal branch, the principal branch. Okay, So here, we choose the principal branch. To name or to define Z to be. Here, for whatever a composition, you can say that, but usually we do not call it Z to be. Okay. All right, and we know that natural log and logarithm function is a principal branch of logarithm function is analytic, composed with multiplications analytic, and composed with a exponential function is still analytic. So we know Z to be is analytic. Okay. All right. Well, let's just try it. Try to understand this definition. For example, let's see I to I. Let's see what is this number? I to I means exponential of b is I, so it's I log I. Okay, I to I is exponential b times log I. What is log I? Log, remember, it's a log r plus I theta. R is a modulus of I. Modulus of I is 1. Log 1 is 0. So there's no real part. I, the argument of I is pi over 2, right? So it's just pi over 2 times I. Right? Log I is pi over 2 times I. You only have the imaginary part. There's no real part. All right? And then I times I is negative 1. So it's exponential of negative pi over 2. And this is just it. It's just e to negative pi over 2. There's nothing to simplify it, right? If you have a complex number, of course, you can simplify it. But if you have a real number, the complex exponential function, the real exponential function, they agree for the real numbers. So that's it. That's it. Well, from here you can see that log I is pi over 2 times I. What happen if we change this? For example, let's say 2 to I. 2 to I. What is 2 to I? Exponential. No. I is this b. Yes. Exponential. Here's I. Still I. Here's a log 2. Okay, log 2 is log 2. All right, but exponential of ei theta is cosine theta plus I sine theta. Remember that? So this is a pure, this is called Euler identity. So it's a cosine log 2 plus I sine log 2, whatever number it is, right? Okay. Yeah, that's it. Very nice. Well, let's see the next. In the argument, we always say we need an open set when we try to do the differentiation. But if you want to get any constant, it has to be the argument should be over the connected set. right? Because only over the constant, only over the connected set, you may have certain constant. Otherwise, that constant will depend on the connected component. So because of that, we have the following definition. Region. A region is an open connected subset of C. So later we will always say, okay, let f be a function on a region G of C. Whenever you see the word region, it is open and connected. Okay, region means open and connected. It's like the interval, open interval. All right. Okay, next let's try to discuss the so-called the Cauchy Riemann equations, Cauchy-Riemann equations. All right. Cauchy-Riemann equations are the study between the real differentiation and the complex differentiation. Real differentiation and the complex differentiation. Okay. So let G be G from F. No, sorry. Let F from B from let F from G to C be analytic. Okay, we have analytic function, and F is take the complex value. So F has real and imaginary values. So let uxy to be the real part of fx plus iy, and vxy is the imaginary part of the value f plus iy for z equal to x plus iy in G. Okay, so here we consider G and C are both two-dimensional vector spaces. Two-dimensional vector spaces. Okay, so x plus iy, c u plus iv. Okay, so remember here, z is x plus iy, f is u plus iv, so they are both two-dimensional. Okay, for the two-dimensional stuff, remember that when we get the derivative, the derivative is this way. The limit h approaching 0, f of z plus h minus f of z over h. We said this h will approach 0 from whatever direction or whatever way you have the limit, then that is defined to be the derivative of f at z. So now we are going to choose two different ways. We choose two different ways. The first one, h approaches 0 through the real values. Okay, h approaches 0 through the real value. H, you see, here h can go this way to 0. H can go this way to 0. H can go this way to 0, or whatever way, or even get the rotation to 0. Okay, so this is a possibility. When we have the strong condition. When this limit exists, so it doesn't matter which way you choose. So here we choose h to be horizontal. Okay, if h approaches 0, then z plus h, z is x plus iy. It's actually x plus h plus iy. Okay? It's x plus h and then plus iy, because h does not contribute y part. All right, well, let's see. The f z plus h minus f of z over h. So it is f x plus h plus iy minus f of x plus iy over h. And remember, f is u plus iv. So u, in this case, it becomes u of x plus h y comma y. This is a u. And iv, v of x plus h comma y. This is v. A minus, sorry, not x, parenthesis, u of x y plus iv of x y over h. Right? And let's separate u and v. You separate u, you get u x plus h y minus u x y over h plus I, and then you copy v of x plus h y minus v of x comma y and over h. Right? So in this computation, you see that when h approaches 0, y is always fixed. So f prime of z, in this case, h approaches 0, h is real. It's actually the limit of this part, u x plus h y minus u x y over h plus I v of x plus h comma y minus v of x y over h. Use a bracket. And this is exactly the definition of a partial derivative with respect to x. This is a partial derivative with respect to x also. So this is a partial u, partial x evaluated at xy plus I partial v, partial x evaluated at xy. We evaluate at this fixed point, right? Okay, that's the complete computation. How do we come up with this? See it? So in the short, it is a ux plus ivx in the short notation. Ux plus ivx. Here this x means we do the partial derivative, and we still evaluate at xy. Xy correspond to z. Z is x plus iy. Okay, so this is a first way to evaluate the derivative. Now let's see the second way. So h approaches 0 through the imaginary axis. Vertically. This way, vertically. Vertically. So how do we make sure it is vertically? We get h is real, and we use hi. H is a real number, but h times I becomes a pure imaginary number, right? So, let's see. The fx plus hi, no, sorry, f of z plus hi minus f of z over hi. Here h is real. In this case, h is still real. And we almost repeat this process. This is f of x plus iy plus ih minus f of x plus iy. Z is x plus iy over ih, whatever. Okay, and then here, this is x. The corresponding y part becomes y plus h. So if we write as uv, this is a u x comma y plus h plus I v parenthesis x comma y plus h minus u x comma y minus I v x comma y over hi over hi, and then we separate them u and v. So u x comma y plus h minus u x comma y over hi. Be careful, there's small change here. Plus I v x comma h plus y plus h minus y v of x y over hi. Okay, so the denominator is hi. H is real. H is real. So by this form, we guarantee we choose a pure imaginary number. And then you see here, this I and this I, they're cancelled. And this denominator I, when flipped to the numerator, the reciprocal of I is negative I. So you actually have negative I u x comma y plus h minus u x comma y over h plus vx comma x y plus h minus vx comma y over h. See it? And then you let h approach 0. A pure imaginary number approaches 0 if and only if it's the real coefficient approaches 0, right? So the limit hi approaches 0, h is real, is exactly this part. Let me copy it, make it complete. Vx comma y over h. See it? Okay, and this is exactly the partial derivative of u with respect to y. X is fixed. Here's the partial derivative of v with respect to y. But here's a negative I partial u partial y evaluated at xy plus partial v partial y evaluated at xy. Right? That's the same process, but you just allow h approach 0 either along the real part or along the imaginary part, imaginary numbers. And because they both give us the f prime of z, so definitely they equal to each other. So this, let's write it. This is a vy minus I uy, v sub y, partial derivative with respect to y, minus I u sub y. Okay, so you compare them. This is ux plus ivx. This is a vy minus iuy. So we have partial u partial x. The real part is equal to partial v partial y. And this partial v partial x is equal to negative partial u partial y. These two equations together They are called the Cauchy-Riemann equation. They are together called Cauchy-Riemann equations. All right? For an analytic function or for a differentiable function, definitely u and v are differentiable. If you have a differentiable, complex differentiable functions, both equations make sense. Okay? Both equations should make sense. All right, so be careful. This set is called the Cauchy-Riemann equation. You have the corollary, but that is not a Cauchy-Riemann equation. This one. So ux is vy, vx is negative uy. So ux is vy, vx is negative uy. Okay, so after the first differential equation, after the first partial derivative, we cannot automatically take the second differential derivative. The second partial, well, what did I say? After the first partial derivative, we cannot automatically take the second partial derivatives because we have no idea if they are differentiable or not. So here, that's why we say, suppose uv have continuous second partial derivatives. Okay, assume we can do them and they are nice, continuous second partial derivative. Okay, continuous second partial derivative, let's start from here. We start from ux equal to vy. We differentiate again with respect to what? Yeah, with respect to x. Let's say with respect to x. So we'll get the second derivative. So it's like this, right? Just keep writing on the left-hand side. Okay, and the other one, so partial v partial x is negative partial u partial y. We can move negative sign to the other side. So partial v partial x is negative partial v partial x is partial u partial y. And then we differentiate with respect to the y. Differentiate this equation with respect to y. So it's negative partial y partial x is partial u squared partial y squared. Okay? Because we assume they have continuous second partial derivatives, partial x partial y partial x, the mixed second partial derivatives do not depend on the orders of x and y. So they equal to each other, but with the opposite sign. So we add them, that's 0. So adding them, we have partial u squared, partial square u partial x squared, and plus partial square u partial y squared is equal to 0. You add the left side and right side, this middle part, the sum is 0. Okay? So we come up with this one. And okay, this is one thing. So we have a definition. Any function, not necessarily come from the differentiable function. Any function with continuous second partial derivatives. Yeah, partial derivatives. Partial derivatives satisfying. In the book, they label them as a 2.25. Satisfying 2.25 is said to be, if we just give a name, harmonic. Okay, so it actually tells us the real part of a differentiable function f is a harmonic function. Actually, when you have this f must be analytic. The real part of analytic function is harmonic. So u is harmonic. U is harmonic. U is harmonic. Actually, with a similar, almost identical computation, we can see V is harmonic because from here, we differentiate with respect to, this is a partial x. We differentiate with respect to y. So partial square u, partial y, partial x. In this one, we are going to copy it as a, we differentiate with respect to x. So we'll get partial v squared partial x squared is equal to, then we use the original one. So it's a negative partial u squared partial x partial y. And then same thing. We add these two equations. They equal to this sum is 0, and you will get the same result or same conclusion. The v part, the imaginary part of the analytic function, is also harmonic. Is also harmonic. Okay? Okay, so from analytic function, we get two harmonic functions. And counterpart, from harmonic functions, we can get analytic functions. Okay, so we are going to present that direction in the next video. Okay, the lecture is not finished. Okay, thank you. We will continue in the next video.